very pleased to introduce Maggie, who's going to be talking about counting the undercounted, network scale-up methods for estimating hidden populations. As we've done in previous semesters, we're going to use this slido.com for questions, and Chak-Fung and Candice will monitor the questions, and then at the end, we'll have the Q&A. So if you have questions during the talk, after the talk, go to slido.com and enter this code, and that will be the Q&A session for this public lecture. So with no further ado, Maggie, take it away.
Thank you. Can people hear me fine? Okay, great. Good afternoon, everyone. Thank you for coming to the public lecture. And today, instead of because this is not a job talk, so instead of showing like very technical muscles, I'm gonna try to introduce you to a area of problems that I hope by the end of the talk you feel like this is an interesting and also important field to work in. This is a collaboration. This work consists of several projects. That's a collaboration with Ian, Le, and Charles. Now it's not working.
Click once. On the mouse itself.
Oh, on the mouse. Okay. Okay. So last year, a New York Times reporter contacted me, asking me to comment on the statistical validity of a report, which is the report on the right. It's called Scale of Harm. The report was trying to estimate the prevalence of trafficking to produce child sexual exploration material in the Philippines. And predated the report on the right was a 2020 report done by the IJM, which stands for International Justice Mission. So the IJM 2020 found that the online sexual exploration of children was usually, so this is Philippines, was the largest known source of OSEC cases. And moreover, they found this is usually a family-based crime. And without intervention, this abuse usually lasted for years. And customers tended to be older men from Western countries. And also, traffickers tended to be younger Filipino women, often family members of the victims. So this is some crime that the Philippine government and also United Nations, UNICEF, trying to stop. And this is very severe and very shocking on children. So that's why to do anything, we first have to know the scale of the harm. That's why they wanted to do such a report. They want to find out how many children are exploited every year. And is there more now compared to before? Who is committing them? And as you can imagine, this kind of crime, if you rely on the only available data source, which is reporting, this is very hard to count because according to numbers they collected, only 0 to 4% of victims ever reported the crime. And only 0 to 3% of them know how to report them. So this is almost impossible to be done just by regular method. More generally, outside this particular case, there are many such groups that we call hidden populations. Sometimes refer them as hard to reach or hard to sample populations. Examples include like the trafficked victims we just talked about, also includes people like drug users or illegal immigrants. So common statistical method or survey sampling methods would fail in counting the number of these groups. Firstly, because they're impossible to reach. And the second, because usually these groups, or sometimes these groups, are stigmatized. So the members tend to hide their membership. Therefore, if you run a regular survey sampling, you're not going to be able to count them and get them. And we usually say invisible populations remain invisible in policy. However, they're very important in public policy planning and public health planning. So we need to know their sizes to assess the issue, to understand the scale. So that's why statistical methods are helpful here. Traditionally, commonly used methods to count these hard-to-reach populations, including enumeration, which essentially means you need to find someone who's really knowledgeable of this group of people, and they're just gonna sit down and tell you how many there are, or they even tell you exactly who are in the group. The second one that's more statistical oriented is called capture-recapture. This method came from the ecology domain, which scientists use to count animals, right? You catch a group of animals, you mark them, you release them into the forest, and then after a while, you catch them again, and then you count how many of them that you catch in the second wave has the mark that you previously caught. So based on that intersection, you essentially back calculate the population size. There are many assumptions behind this method. The third one is more recent. It's called respondent-driven sampling. This is using people's connections through people. This is essentially you start from a seed, which is several people who are in the group, and you interview them. Then you give them coupons and ask them to distribute to their peers who are also in this group. You ask those people to come in and then take the interviews, and then wave after wave. Sometimes more generally, this is called link tracing method. As you can see, all the three above methods, you need access into this particular group, right? You need people who either know the hidden population really, really well, or who are in this hidden population themselves, so that to start counting. But in many situations, we actually do not have any access to the hidden population. We don't have a seed, right? For example, in the trafficked victims, usually they're still being trafficked. You can't really just find anyone and interview them. And also, to be more extreme, people who have already died, that is becoming an impossible to reach population, which is actually where this method started. This method started from the 1985 Mexico City earthquake. During that time, the original authors for this method were actually just happened to be in Mexico City. And right after the earthquake, different government agencies released the death toll very differently. Sometimes the numbers differed by magnitudes. And so these authors, these are all social scientists, they started wondering, is there a truth? How many people actually died in the earthquake? And what they noticed is that a lot of the people they talked to mentioned they know someone who died in the earthquake. So based on that conversation and that thought, they thought about, well, how about I utilize that information instead of directly counting? Can I do an indirect counting? So traditional network data looks like the one on the left, that we collect people's connection. We know 1 and 5 are connected, 1 and 2 are connected. We know who is connected with whom. But instead of collecting traditional network data that requires very detailed and personalized information, now instead, we can have this kind of different data type, which is, I'm just gonna ask you, how many people do you know who are in this group? For example, I'm gonna ask you, how many people do you know who are named John? How many people do you know who are age 15 and above? How many people do you know who are drug users? So usually in this kind of survey, they're gonna put several of the groups that we do have a true counts, and then put the unknown population we're interested in estimating in the end. So the way we call this type of data aggregated relational data, because instead of having individual network relations, we aggregate people's relationship into the total counts for a particular group. So the authors, because they heard so many people talk about they know someone, so they thought about, well, how about I use the network people have to create something innovative, clever, so that I can scale up each individual's personal network to the entire population. The key idea behind the network scale-up method is actually very simple, which is this one-line equation. So we use YIK to denote how many people respondent I knows for group K. And we use DI to denote the respondent I's personal network size. Essentially, this is saying the proportion that in your own network, how many people belong to this group is the same in the entire population. So I can scale that up to the population version, which capital NK would be the quantity we're interested in. This is essentially the key idea behind this whole method. Instead of using directly counting, I'm just going to ask representative samples, ask people, how many people do you know who are in this group? And I use this relationship to estimate the entire population. So this is a very clever idea. So the social scientists then started, as you can see, from the time they thought about the problem to all the way they came up with actually the method took quite a few years. And then they came up with the initial binomial model, and they use the MLE to estimate these parameters. This is slightly different than the traditional binomial likelihood estimator if you've ever done it, because in this case, both the DI, which usually we call N, and the P, which is NK over N, are unknown. So that's why we need the populations of those we call known populations, which usually you can get from census. For example, how many people are aged 15 and above? From name registry, you can get how many people are named John, say in the US. So those would be known populations. Using those known populations, we're going to first estimate personal network size, which is the DI parameter. And then plugging this in, they estimate the unknown NKs. So that's their way, the two-step estimator is their way of estimating the parameter. This picture, this slide, single slide here, is still used. This is still the most commonly used network scale estimator. But as you can see, for this to work, you need a lot of assumptions, right? This is the ideal world. So there are three key conditions to make this work. The very first one is called random mixing, which essentially says everyone in the population is equally likely to know someone in the subpopulation. People are missing randomly. You need that to have the constant proportion assumption. And the second one is called perfect knowledge, which essentially says if someone, my friend, is in that group, I know he's in that group. So this is called perfect knowledge. And the third condition is accurate response, which means usually these are done by surveys or questionnaires. Like the respondents have to be able to answer the question within, say, 30 seconds to accurately recall, I know 30 people who named John, right? So these are the three key assumptions in order for that binomial model or that equation to work. We're all statisticians, as we can imagine. That's definitely not going to work, right? But this is a very clever idea. So, however, the numbers came out largely off. And because of these three conditions, so usually these kind of survey data are subject to four main biases. The first one, we call it barrier effects, which essentially violate the random mixing assumption, which essentially says respondents can be more or less likely to know someone in a particular population due to their own characteristics and also due to the population's feature. And it can be geographical, and it doesn't have to be geographical, it can be just nature. So for example, the number of Native Americans you know highly depends on where you are, right? Which state you reside in. But on the other hand, the number of professors you know, it doesn't really matter where you are, but it probably matters who you are. So without the barrier effects essentially violates that constant proportion assumption, which essentially means I cannot just simply scale up my network and your network and everyone's network the same way because our networks look differently. It doesn't always equal to the population network. And it's not limited to the hard-to-reach population. So, there's no way that you can directly estimate the barrier effects because you need to study personal characteristics and population characteristics carefully. And you need to do that for population to population and person to person. So there's no direct way you can just estimate that effects. The second bias is called transmission error, which essentially violates that perfect knowledge assumption, which would saying like, even if I have friend, I probably don't know everything about my friend. And this also doesn't just exist in the key population or in the hard-to-reach population. Sometimes a lot of the easy-to-reach population is also subject to this bias. For example, study shows that a large percentage of diabetics, twins, and so on, they don't actually tell you they're twins. And like some of our colleagues I've known for many years, I learned about like she's a twin, like many years later, right? People don't just tell you that. And but transmission error, you can actually try to estimate this error by interviewing people who are in the group. Essentially, you are trying to estimate a visibility factor, or you can interview directly how likely do you tell your friends, right, that you are in this group. By trying to estimate this visibility factor, we can somehow correct this bias. The third one is the recall bias. It's because people only have limited time to remember all the names they could think of, right? And there's actually very little research has been done that how many people respondents can recall within certain time period. And this is a bias that's also going to increase as the survey progress. As you can imagine, if I ask you 40 questions about different people, how many people name this, age, have children, married, and all the things, towards the end of the survey, you're going to remember vaguely and vaguely. You're going to start guessing, right? Also, people tend to overcount the number of people they know for small population or rare events. If someone's in a car accident, you're going to remember it vividly, and you're probably going to overcount them. But if I'm just asking you a name, and it's a very common name, you're very likely going to undercount it. And also, you're more likely going to round it. For smaller population, people tend to enumerate. And for larger population, people tend to just round the two by guess, right? So these all generate all sorts of errors. And there's actually very little that has been done to try to reduce this particular recall bias. Finally, it's not particular to network scale-up survey. It's actually common for any social science surveys, which is the response bias, that the respondents probably will deliberately misreporting the number of individuals they know in the subpopulation. It highly depends on how you design your survey. For example, if you want to ask how many female sex workers do you know, to a husband in the household setting, the husband probably going to say 0. And which means we actually don't know how many essentially they know, right? So that essentially says this is not a very good way of collecting such information. But this can be reasonably reduced at the data collection stage by carefully designing your survey, your method, your location, and how you're going to interview people. Okay, so as you can see, this is a very promising method. However, this method is very likely to generate data that has huge errors and a lot of problems, right? A lot of noise. And which is actually, to me, this is an opportunity for statistician. And after that 98 paper came out, 80 years later, the very first group of statisticians came into this field. And up until now, still, there are only probably 2 groups of statisticians who have worked in this problem, this paper and the second paper. These 2 papers look at the problems very differently. The very first Bayesian model, we call the overdispersion model, just essentially look at the phenomenon, which essentially says the original binomial model is way too simple, right? All the biases we talk about essentially generate larger variances than the binomial model can handle. Therefore, let's just model the overdispersion. So I don't really care about what generated the overdispersion. What I can do is, instead of saying I have that mean variance relationship from the binomial model, I'm just going to bump it up to allow I have overdispersion. So they essentially put a gamma prior onto that residual parameter. And they came up this negative binomial model, which we know is actually for overdispersed binomial. So that's essentially the simple idea behind this very first version. And another almost 10 years later, another group of statisticians came in, and they come from a very different perspective. They were very ambitious. They were trying to actually model the difference biases. They really want to just model response. No, actually, they want to model transmission, barrier, and recall separately. However, as we've already mentioned, there are no data for them, right? There are very rarely any data. So both of these models are Bayesians. Therefore, the second group of statisticians, essentially, they just assume a bunch of priors from different studies, from existing expert knowledge. Based on those, by assuming different priors into this decomposition of the error structure, they essentially say, I can actually model the biases. Therefore, I've corrected for them. The problem for this paper is that they're way too ambitious, that their algorithm doesn't actually converge. So only a very subset of the model works. So but by now, these are the only 2 groups of, so far, statisticians that have ever worked on this problem, in addition to all the social scientists who've been in this field for a while. So this is where I got interested in this problem, because I really like those simple ideas. I like the beauty of how simple and clever that idea is. And statisticians, we embrace errors. We love variances and noises, right? That's what we do. So I think there's a lot of potential for this particular method. We just have to be able to model them better. And so our idea essentially for this, for the existing data is essentially, you think about the reason that the second group, the model didn't work, is they try to make everything through priors. However, as we know more about these biases, we know these biases actually depend on something observable, which are individuals' characteristic as well as subpopulations features. Therefore, we can just incorporate these into the model as predictors, right? So that's going to actually have more systematically correct the biases. And another observation is all these populations, they're actually not independent. They're actually dependent of each other. If I know more people who are female, age 15 to 17, I probably will know more male who are in that age group, right? Which essentially says I know a lot of teenagers. So some of the groups are correlated. So we should actually also utilize this correlation structure. So that's the idea of this first model. So I'm gonna today introduce 3 different directions for this line of work, but without going into too much detail about exactly the technical details for each model. The first model essentially is just what I said. In addition to modeling the error, having the delta, the degree, and the prevalence, we also put group-specific or person-specific characteristics and group-specific characteristics into the model. And we also assume that your error terms are correlated across groups. That's essentially the model. And this model, can be seen actually as an umbrella model for all the previous models. So if you don't have any predictors and you don't have this residual, this is essentially the original binomial model, the frequentist binomial model by social scientists. If you don't have any predictors and your residual doesn't have correlation, then this is essentially the first Bayesian model, which is the over-dispersion model. The only difference is the shape of the prior distribution. If you don't have any predictors, but in the BIK, you assume certain structures, this recovers the second Bayesian model, which is the decomposing the bias model. So our model essentially can be seen as an umbrella for all the previous models, and it has more flexibility, especially given that in later years, when people collect the N-sum surveys, they started collecting personal characteristics and sometimes group-specific characteristics. So we applied that correlated model to the Ukraine key population study data example. So I will not go into the details for what this data is about, but I want to show you what the data usually looks like. So the top one is the data that's for the male group 20 to 30. This is essentially, the survey asked about 8,000 respondents. How many people do you know who are male between 20 and 30 years old? So that's the shape. This is a very typical Poisson kind of data, right? That looks pretty good, right? And this one is divorced man in 2008. So which you're going to see now we have a higher count of 0 and a long tail. Now we started showing the overdispersion. If we go into the 4 unknown populations that the researchers are interested in, you're going to see, well, we actually don't have much information, right? Majority of people say they don't know anything. And some people would say they know a lot. And for some group, at most, people know 3. So the data quality and also the amount of information vary greatly. And also, you're going to see these populations, and especially like this one, will be extremely hard to estimate without any help from other variables and the groups. So another difficulty in this line of research is we don't have the ground truth. So there's no way we can say, oh, our model outperformed other models, blah, blah. Because the problem is there. We actually don't know how many actually are there. And there are no existing methods that can be treated as a gold standard. So a lot need to be taken into consideration in terms of how we diagnose our model, how we do model prediction checks, how we do model diagnostics. And also, you will have to try to find some benchmark that you think are more credible. For example, in this application to the Ukraine data, the numbers we produce is the first column. You can see it's almost doubled, sometimes tripled, the numbers that use the original binomial likelihood method, which is still by now the most commonly used method in this line of research. And so if you see this number and what the report actually published, you're going to see, oh gosh, we overestimated the count, right? However, the Ukraine government also do not believe this column of numbers. They think they undercounted. Therefore, they usually do some ad hoc adjustment. And so the last column is in their official report, their post adjustment, which they believe is closer to the truth by whatever standard. And you can see that our model produced the number is way closer to this actually adjusted number compared to the original number. Of course, this cannot prove that the model is reliable. However, it does offer some validation to the method. In addition, we can offer some insights into the particular population and also the respondents that the survey collected. For example, we learned that people who actually are Ukraine citizen tend to know more people, and who are employed tend to have a larger network size, and people who have secondary education and above tend to have a larger network size. So we can learn something about the respondents a little bit. And also, one of the key features for the Ukraine data is that they have this level of respect variable for each of the population they ask about. This is a very important variable that offers some insight into the population-specific features. And it turns out this is a very important factor. The more respect people have to each population, the more people you tend to know about that population. So this result is consistent with our expectation, which also all of these, and finally, is this correlation plot. This essentially helps us in the sense that we learned about, well, we actually know very few about the left corner, which is the unknown groups. But this is the group that we want to understand. However, as you see from the original data, there's very little information. But what we can find is this group is also highly, for example, the IDU group, the injected drug users, is also highly correlated with prisoners. And this is a group we actually have an accurate count. And we can also find some other interesting correlations. Well, some of the correlations are expected. For example, if you know more people who are, if you know more female who are 15 to 17, you are going to know more male. Some of them are expected, but some of them you also learn that, for example, some of the negative correlations. If you actually know the younger people, you're actually less likely to know people who are named Pavlo. And if you dig into that, Pavlo is in Ukraine is actually an old generation name. So these are the kind of structure that the model can provide. How does it help? It's going to help you to design future surveys, to think about what kind of questions you want to ask in your survey, which groups you want to ask about, right? Because we know so little about the unknown population, maybe we can ask more people about the other correlated groups to the unknown population so that we can borrow some information from this group to this group. So that's how why we think it's helpful. Okay, so I want to now move on to some ongoing research, which is, so the traditional NSUM survey, I've been hand-waving about, we've been asking the question, how many people do you know? But the word know actually has a lot of meanings, right? Usually in the survey, they say the know definition is you recognize the people by name and by sight. So which really is just that you know this person. And the social scientists started to find that because of all the issues we see, like you can see that there are very little information in a lot of the groups that we're interested in. No is a too vague and also too distant measure, which means probably that type is too weak. They started thinking about how about we ask for a stronger type. Rather than asking general knowing, general acquaintances, I'm asking for a more closer relationship. Therefore, the respondents will know more about the people they're asking about, right? So they started to implement and experimenting this first in 2016. And they did a Rwanda study that they randomized the respondents into two groups. One group, they asked about still the traditional knowing definition. The other group, they ask about, by knowing, you have to have shared a meal with this person within the last 12 months. This is a much stronger type and a much stricter definition. And later on, in 2022, they conducted a Vietnam study that they asked for 4 different tie strengths. Any acquaintances, interaction within the 12 months, sharing a meal within the past 12 months, and sharing a meal within the past month. So from weakest to strongest tie. And another study is Andrew Gellman conducted back in 2021. His purpose wasn't trying to estimate any of the key populations. His purpose is actually he's inventing a new notion that who you vote for depends on your close circle, your close connection. But as a byproduct, he produced this data set that he actually asked the respondents 3 types of ties: family members, close friends, and all other acquaintances. They are all subsets of each other. So these are so far the only 3 data sources that have different tie strength. So for these 2, they're the same group of social scientists. Their hypothesis is that, well, there must be a trade-off. If I ask for the weaker definition, I'm going to get a larger sample, right? I'm going to get a larger size. However, I'm going to have larger error because people actually know relatively little about the weak ties. If I ask for a stronger tie, I'm going to get a smaller sample. However, my information about that sample will be more accurate. Therefore, they hypothesized that the total error should have this curved relationship, and there is an optimal point. And they think these total error can be decomposed into non-sampling and sampling. And the sampling error goes down as you go to a weaker tie, and the non-sampling error goes up. And there should be a balance. They call that a quality versus a quantity balance trade-off. So as a statistician, we can translate this problem into a very classical bias variance trade-off problem, right? This is essentially saying for a weaker tie, you're going to have a larger sample size, so you will have a smaller variance. However, you probably are prone to a larger bias. And on the other hand, if you have a smaller, stronger tie, you're going to have less bias. However, because the sample size is smaller, you're going to have a larger variance. So we should also see, I can translate that problem into a minimizing MSE problem, right? Therefore, so we essentially put on some of the very general form to the original equation and then derive the MSE and run some simulation. We actually got a very similar shape of curve, which essentially says, yes, there should be an optimal point. And this line of research is trying to design a pilot study to learn about whether I have an optimal strength so that later on in my actual study, I'm going to just ask about the knowing definition using the optimal strength. So that's this line of research. But to me, this is not good enough, right? This is wasting data. If you pick a particular definition, you throw away all 3 other definitions. You throw away 3/4 of your data, right? So why not use all? So this is the ongoing work, which essentially I'm very ambitious and greedy. I want to use all of the data, but we're also estimating the same common parameter, which is the population prevalence for each of the subgroups, right? So how about I use all definitions? I will treat that as a multi-layer network data, which is coming back to what I do in my other research. And this model essentially is just a multi-layer latent space model that you would have each individual, your degree will depend on the definition or the tie strength, right? I'm going to have a larger network if you ask me about who I just know. But I'm going to have a much smaller network size if you ask me who I had meals in the past month. But we're all estimating the same common prevalence in the population. And then, so this is a latent space representation, which essentially says people, when we have social network, our connection is actually dependent on our latent position in a space that's not observable. And if my position is close to yours, then we're more likely to make friends or be connected. If my position is farther away from yours, then we're less likely to be connected. In this case, this inner product measures each individual's position and each population or group's position. So the inner product between these two measures how similar I am to that particular group. If I'm closer to some group, I would actually know more people in that group. If I'm farther away, I'm going to know fewer people in that group. So these are the graphical representations for this problem, and Charles produced this problem, this graph. Thank you. This is the 4 definitions in the Vietnam study that the black dots, numbered dots, are the populations. In the Vietnam study, there are 19 populations they are working on. And the red dots are the respondents. And there are about 500 respondents. And you can see that if some red dots are closer to a particular group, that essentially represents these group of people know more people in this group. And if 2 groups are close together, that means these 2 groups are similar in some sense, so that people who know people in this group will also more likely to know people in this group. And if you look at these 4 representations, you're going to see a lot of similarities across different layers. For example, some of the things make sense. Like, for example, group 2, it's always on the opposite side of group 11 and the 10, which means the group of people who know lawyers probably are very different than the group of people who know farmers and builders. These are essentially 2 different groups of people. And this relationship is consistent across different layers. This is sort of evidence that we should be able to build a joint model utilizing all layers of data so that we're not wasting any information. So this is still ongoing work. And another recently enriched type of data is spatial and temporal data. So when people ask, especially when we go into the meal definition, when I ask you how many people have you shared a meal with in the past month or so, even though my underlying goal is to estimate the national prevalence, we're essentially asking about local, because more likely the people who have shared a meal with you are from your local area. So this is an omitted problem in the past. Therefore, we are thinking about, well, instead of saying that, well, the underlying assumption, of course, when we are still trying to pretend this is asking for national, this is essentially assuming that it's homogeneous. No matter where you are, it's the same prevalence. However, usually this is not true, and we have some evidence across regions, the prevalence can vary a lot. Therefore, with the newly available data, we can actually build a spatial model for the ARD data. In addition, like one of the goals in the Philippines study was to monitor the trend. They want to know whether this crime is getting more prevalent or less prevalent over time, right? So through time, once we collect more and more data, we can build a temporal ARD model. So a spatial and a temporal ARD model is also an ongoing project. Okay, so coming back to the beginning. So the finding in the scale of harm report actually says nearly 500,000 Filipino children, which is 1 in every 100, were trafficked to produce new child sexual exploitation material just in the single year of 2022. And nearly a quarter of adults, that's 3 out of 1,000, trafficked the children to produce new child sexual exploration material in 2022. This number is shockingly high. That's why the reporter wants to know how accurate or how reliable the numbers can be, because this number differed quite a lot from the IJM 2020 finding, which that report was based on capture recapture. And this is the very first report that's based on network scale-up method. That particular study was very carefully designed. They had a pilot round. The reason it works to interview other people about this kind of crime was due to the special nature in villages. Your neighbors know a lot about what's going on in the rest of the families in the villages. That's why in their pilot study, they learned a lot about what are the kind of languages they should use to ask the question so that they understand the best. and how much knowledge they do have for the other people in their village. So in some sense, I have high confidence that this particular method is very credible in this case. However, I don't actually know exactly the details. Their data are not publicly available. But what I want to say here is what I've shown you today is actually the very first step of how statistics and how we can help to protect the vulnerable people. And the numbers that we work with every day, they're not just data. They're actually decisions, they are resources, and their lives. So thank you.
Thank you, Maggie. So if you have any questions, it's not too late to still submit them at slido.com using the code 3156959. But do we have any questions in the room? Yeah, we have one back.
This is very, very interesting work. Your conclusions, you have a hierarchical method, so it should be possible to produce pretty good uncertainties. So what are the uncertainties you have associated with your numbers at the end, and how much do you trust your uncertainties in this very complicated sort of the setup that you have?
For my model or this one, or the Philippine findings? So for the model that I worked on, we did a lot of diagnostics. So we have relatively high confidence. And also we recognize the situation it works and the situations is probably lack of it. We did a lot of posterior predictive checks. We did a lot of model diagnostics. For this study, they the paper is now published. So in addition to the report, they now have a technical paper that published in JRSSC. They used a relatively easier model, but still taking into consideration of a lot of factors. So I would say I actually believe the numbers, the true numbers are closer to what they produce in this new report compared to the previous version. But I don't actually know the exact number or the exact credibility for that. Does that answer your question?
So thank you for your answer. So there is a question from the Slido. Like in the very beginning, you said that it's very difficult to count the number of data because there are only 0 to 4% are reported. So how reliable is this estimate, like 0 to 4%?
Oh, so that was one before people try to estimate these numbers purely based on reporting. If there is a case, it's been reported, then this year, if there are 5 cases that are reported, then by the end of 2022, they're going to say 5. But the new method, the network scale-up method, doesn't rely on victim reporting it themselves. That's actually the attractive feature for this method. This is an indirect counting, that it doesn't require the victim themselves to report, but relying on other people having knowledge of the crime.
Any other? If not, I have a follow-up question to that. So if you know that 0 to 4% of people get reported, and you know like the general population size, and you have these 5 reported people, wouldn't you just be able to reverse engineer that?
So the 0 to 4% is also not a very accurate count, right? If you don't know the actual number, how do you get the 0 to 4%? That's also an estimate. Yes, you can get the reported number, and you can also get a separate guess of the percentage of reported, and then you bump it up by that factor. That's another way, right? But the fact that you can accurately estimate the percentage of reporting is actually very hard. So that 0 to 4% was also based on some previous finding that's not very statistical sound because we simply just don't have the data.
Okay, I also have one more question. On the scatter plots for the survey respondents in the latent space, so the red dots are survey respondents, but what are the black points? Are those aren't actual, those aren't representing actual.
Those are the
Those are-
groups. Those are the populations we're interested in studying. Essentially, that represents the group's location. If you think of the group as group of people, that's their center.
So is that the like a centroid from a cluster? Like what actually is
This is the dots are the groups, because the groups in the aggregated relational data, for the groups, you don't have individual people in there. It's just a notion that that's the group of people who are 17 to 19, for example, or who are lawyers, doctors. So essentially, this is just the number 1. Well, this is hidden, but for example, number 10, this is just farmers. That represents the group.
Okay, any final questions?
Yeah, there's one more question from the slide though. So this audience asked that if there are any setting where you have something close to the ground truth, so how do you convince the people that the truth of your model, especially for the sensitive topic?
So the question is if there is a ground truth.
Yeah, like if there is any sample that you know the ground truth, so that like you can validate that your model do a good job on that.
Yes. So for all of these models, like this is also related to Merle's question. So for example, in the Ukraine study, we have the population counts, the actual counts for these groups that we call known groups, right? So one way to validate is that you also estimate these groups and you see how close your estimates are to the actual numbers, right? Those were taken as ground truth. But one problem with that is the behavior of these groups are very different to the behavior of these groups. Even if we can do a pretty good job in these groups, doesn't guarantee we're gonna do a pretty good job in this group, right? So if in the future we're gonna have ground truth for any of these groups, then you would do the same thing. You would essentially still estimate them and compare your estimated value to the true value, right? But at this moment, these are called hidden populations because we don't have a gold standard estimates.
Okay, if there are no more questions, we can thank our speaker one more time. And there's snacks and